Hello everyone, this is content for Chapter 6, dealing with our rate kinetics. And so far we've covered 0th, first, and second order rate kinetics. And that was in our last video. Now what we really want to focus on is our half-life equation and how to set that up in a logical way using first order rate kinetics. And as you'll recall, our first order rate kinetics would give us our instantaneous concentration is equal to our starting concentration, e to the minus kt, where k is our rate constant and t is time. By definition, the half-life is the amount of time it takes for 1/2 of the starting concentration to react or decay. And so basically what that's saying is that our instantaneous concentration is equal to half of our initial concentration. And it's best to look at this pictorially, so let's go ahead and set that up where we have our time on our x-axis and our concentration of reactant on our y. And since it's first order, we should see some sort of exponential decay in such a fashion. Of course, our initial concentration is right there. And if we allowed half of the molar equivalents to decay, what we'd end up with is some value that is 1/2 A naught. And the amount of time that that takes to occur is T 1/2. T 1/2 is our half-life. And on the other hand, if we had T 1/3, well, that would mean our 1/3 life, or the amount of time it takes for 1/3 of the starting material to react or decay. And so we can just go with that logic to look at a third life lifetime. So now let's go ahead and set up our first order rate kinetics, and remember that that is A equals A naught e to the minus kt. And if we are comparing our instantaneous concentration to our starting concentration, that would be the natural log of A minus the natural log of A naught equals minus kt. And we can rearrange that to just say it's the natural log of the concentration of A over our starting concentration minus kt. Now, our caveat here is that at T 1/2, at our half-life, the instantaneous concentration of A is equal to 1/2 of A naught, and we're going to go ahead and take that definition and insert it into our natural log to yield the natural log of 1/2 A naught over A naught equals minus kt. So with natural log of 1/2 A naught over A equals minus k t, and let's make sure that we put our 1/2 there. On our last slide I forgot to do that, but this is critical for our work. You'll notice that we can go ahead and we can cancel out a naught, yielding the natural log of 0.5 is equal to minus k t 1/2. And we can go ahead and rearrange this algebraically to yield the natural log of 0.5 divided by minus k. And in order to deal with the negative sign, once we have rearranged it and solved for t 1/2, we get the natural log of 2 over k. And let's recall that k is our rate constant for our decay mechanism. Now, why is this significant? Well, we just have the natural log of 2 over k equals t 1/2. And because of the mathematics, you'll notice that our starting concentration, A naught, is not needed. And so for any kind of decay mechanisms, whether or not that is fluorescence, radioactive decay, such as carbon-13 dating that we mentioned in class, or thermal decomposition mechanisms, we can go ahead and actually date everything that we have and basically back calculate out our amount of material, or the actual time in which the material has been decaying, based on just knowing what our overall rate constant is, which can be found through control experiments. And so this is our conclusion for our half-life video. And I hope everybody is having a good weekend, and I will see you very, very soon. Thank you very much.